Good afternoon, good morning again, Louis. Oh, you're muted. You're muted. I was just sharing the timetable, the schedule, and I think we could just cut short the real cases just to have enough room for discussion. Either way, so
Okay.
we have so many real cases that it's okay if instead of 16 we go for 14, and perhaps that way leaving some room for discussion.
Okay, I've got 4.
Perfect. No, that's great.
Welcome back and good afternoon, Mr. Luis and Dr. Manuel, and to all our participants. With the permission of the speaker, shall we start the session?
Yes.
Yes. The floor is yours, Louis.
Okay. This last session, as Manuel said, we're just going to look at a few case histories with regards to embankment dams and then concrete dams. So I'll start off with the embankment dams. And basically, these things that I show here is some of the things that we actually look at if we do look at our monitoring results or our surveillance results. If you work with earthfall, then you basically have time and or water level dependent deformation of the earthfall material. One could have loss of strength. You could have internal erosion or piping. You can have pore pressure increases associated with progressive opening of transverse cracks. You can deal with dispersive materials, and I've talked about that, and you could have problems with foundation. So I'll start with Inyaka Dam, and this is, it's very close to Zoeknog that I discussed yesterday, the dam that failed, that had dispersive material issues with the Morning Glory spillway. And this dam basically have the same issues. So it's the same material. And normally if we build any dam, we normally build a test section to actually optimize the construction procedures. And here you guys can actually see this is a very sensitive clay that we deal with. And if we overcompact it, you guys can see that you get these laminations. So you actually form these basically piping sort of ways as well. You make it actually easier for internal erosion to happen. If one actually looks at the sort of a section along the center line of the dam, then during design, it was actually expected, because you have a concrete section here and then a fairly steep valley section as well, that you most probably will get some arching in these two areas. Okay, so arching means it's the earth will arch, and then below that arch, you most probably will actually have negative effective stresses in your embankment. The other concern always when you actually build earthfall against concrete, you also might actually have some negative effective stresses, and you might have some piping that happens along the So what we installed these clusters of earth pressure cells in the area where we expected the negative earth pressures or the arching. Yes, and some people might say, but you expected it, so why did you install it? Well, if we know it's there, then we can focus and highlight our efforts in that area. Okay, so remember, we're monitoring things where we know we most probably will have issues, and that's why we're monitoring it. So if one just actually looks at the results of the total pressures, and many people make this mistake where they actually just look at the total pressures from the earth pressure shells, just of interest. So the brown here is actually the embankment as it was constructed. The blue is the water level. So if you just look at and the rest are the total earth pressure values. If you look at it, see if there's no issue actually for this particular cluster. But what we need to actually do is we need to take the total pressures, subtract the barometric pressures from that to get effective pressures, and then actually from there go and calculate the principal earth pressure stress, earth pressures. We want principal pressures and not just effective, because that's the other thing that people forget about, and they consider that earthfall is just like only have vertical stresses in it, but that's not true. You actually your principal earth pressures are normally not in a vertical direction. So for this particular one, you guys can actually see, if you go to principal earth pressures, you actually see that you have negative earth pressures there. So, as part of the design, because we expected it, we actually had a very rigorous filter design. And once we've established that that we have negative earth pressures, we also adopted the inspection program in that area. We increased the frequency of that. So yeah, we can actually prove that we have negative principal earth pressures in that area. And this is just one of the presentation methods that you can use. I did this in Excel, but you can actually just see the direction. Even this one, it's difficult to represent the angles, but it's much easier if you actually have something like this, where you can actually see in this particular case, it is vertically is the highest positive principal stress, and in the horizontal direction is the negative earth pressures. But it's not always like this. For that particular point, that is the case. Okay. So my next one is Driekopies. I've got two examples. So this is my so Driekopies. I've talked about it before. I mentioned it, but so it's an earthfall embankment with a concrete spillway in the current river section. But it's very interesting, the site, in that the river through the millennia actually were at different positions. So this whole area here is actually an alluvial floodplain that contains material that was previously a river. Okay, so this is just a typical section from a drawing. And you guys, the other issue was it's a thick alluvial layer. It was first proposed to actually have a clay cutoff, but the client said it's too expensive, and the designers came up with a solution that they had a tube and machete grout curtain there that goes into the solid rock. But it's if I remember correctly, it's like 15 or 20 meter deep alluvial plain. So you've got no other defense against internal erosion, except for on the downstream side, there's pressure relief wells to try and actually draw down the phreatic line here, so that you decrease the risk of piping. Okay, so there's a lot of piezometers installed here. I mean, the other thing is the clay that they used here is very impermeable clay. Okay, so it was of interest to actually know about the dissipation of the pore pressure after construction. And there's also installations upstream and downstream of the grout curtain to see how effective the grout curtain was. So the designers actually they established that basically there was 2 areas of concern, and they focused on those 2 areas of concern. So they didn't go and just install piezometers all over the embankment. They identified 2 specific areas of concern, and they also identify the interface between the concrete and the earthfall as a problem area. So there's basically just 3 sections that is monitored for this particular dam. So let's first look at section number 1. So the interesting thing was this dam started filling in 1999, and during the first filling, actually a boil downstream, about 200 meters downstream of the dam, was noticed. Okay. I'll show you guys now as well. The pressure relief wells were not actually not effective at all that they installed during construction. The interesting thing, the methodology of construction, it's important that one understands the methodology of instruction of this dam. So because of the alluvial layer, it did not have a lot of density, so they decided to actually do dynamic compaction on this alluvial layer as well. But they first installed the pressure relief wells, and then they did the dynamic compaction, and after that they did the grouting, and then they built the embankment on top of that. So it's our conclusion that actually during this dynamic compaction process, the pressure relief wells were actually blocked. They're not functioning. But in any case, soon after they discovered this boil, they went and actually installed a new set of pressure relief wells, and everybody thought that the dam has no problem. Okay. So the issue that one has here is actually internal erosion through the foundation and not really through the dam wall. Okay. So for this particular sort of installation, we have standpipe piezometers, we have pressure relief wells, as I explained, the original ones as well as the new ones, and we monitor those levels as well. We've got vibrating piezometers that I've showed you guys already, and we also monitor the seepage that comes out of the filter system as well as the pressure relief system. Okay. There's just the position as I showed you guys, and I've done the last 2 safety evaluations in 2015 and earlier this year, and it actually, you can't get there. So it's a big concern for me to go and do proper inspections. I'm trying to convince the dam owner to actually clear the vegetation so that one can go and do regular proper inspections. At the moment, if there's more boils, you will not be able to see it with the condition of the vegetation down there. Okay. So if one just actually looks at the results from the piezometers, and I know it's a lot of information on there, but let's just focus on the purple and pink ones. These ones are the ones actually there on top, those ones there. And you guys can actually see, as I said, it's a very impermeable material, and it basically, it's only now after about 20 years that we're actually getting to close to the phreatic line pressure. So we've actually had, since the end of construction, it's more than 20 years, more than 25 years, we've actually still had the build-up of piezometric pressures in the clay from the construction. Okay. And we've highlighted the importance of inspection. So if you go to site, the standpipe piezometers downstream of the toe in this section, you actually see that there's a lot of flow that comes from the standpipe piezometers. All right, so just along, so within 3 meters of this particular standpipe basometer is a pressure relief well that is 3 meters deep. So if you actually, for me, it's pretty obvious that the pressure relief well is actually not functioning, because if you have a standpipe basometer that goes down to a specific permeable layer, this pressure relief well is actually not draining that. If it was working, the water level in the standpipe basometer would have been at the same level as you guys can actually see what the level of the water is in the pressure relief well. There's the new one that's also very close to the surface. Okay, so if one just goes and plot all the results on the section, you guys will actually see on the downstream side. So this is upstream, there's your water level. This is just after construction. You guys will see that you actually still have a high water level in the downstream alluvial layer. The same in 2003, and this is after they've installed this new pressure relief wells. So I come to the conclusion that these pressure relief wells are actually not functioning as intended. And this was a situation earlier this year. So unfortunately, at that section, the grout curtain is not functioning as intended, all right? Neither are the original or the new pressure wells functioning. So I've been trying to convince the dam owner that we have to reactivate or replace these pressure relief wells, and that one has to do very regular, proper inspections in the downstream area. Okay. I quickly want to just show you guys section number 2. There's piezometers, earth pressure cells, settlement cells, and extensometers as well, but I'll just talk about the piezometers and the earth pressure cells. Let's first look at the earth pressure cells. Similar installation and what we did at Inyaka. We also were interested to actually see what the stress situation was there. There you guys can actually see the installation positions, all right? And this is again total earth pressure. Everything looks fine. I don't know if you guys noticed, so this dam owner had issues with the equipment, and the procurement processes are not really good. They've got an automatic system, and I mean, Manuel was talking about it, and then the automatic system breaks down, and then you have these gaps of 2, 3, 4 years, if I can, yeah, and then eventually they get somebody on site that can fix it. They fix it, and then it breaks down within a couple of months. But now they've actually contracted after 2015. I told them they have to get a sort of a long-term contract with a reliable service provider that can actually ensure that they always have access and that there's not these problems that they've had before. Okay. So again, we did the conversion from total to effective to principal stresses. And again, you guys can see that there's actually a couple of places that we experience negative earth pressures. Now, the interesting thing, I'll explain now why we had negative pressures, but if we look at the results of the piezometers, you guys can see a lot lower piezometric levels there on the downstream one. That's what we're actually looking for, and it even decreased. So we conclude our grout curtain that actually sits over here is really effective, and we don't have a high risk of piping or internal erosion. So basically we had at 2 places we had negative earth pressures, and at level 3, the higher one, we had good records, and one can go back there. I was actually working for the consultant that was the designer as a young man during that time, and we figured out that negative principal stress is as a result of pneumatic drilling that the contractor did. For some other reason, the contractor decided to go and do some pneumatic drilling there. So please, I mean, I know it's sort of the industry standard that you please must not do any pneumatic drilling in an earthfill embankment. People still do it. But here is an example that you can actually, that proves that you will get hydraulic fracturing if you go and do pneumatic drilling. And it doesn't disappear. It stays there for the whole lifespan. Okay. So just the final one. This will just take a minute, Manuel. With the interaction, the interface with the concrete, it's also interesting to actually see that. Not a lot of people actually monitor this, but that's one of your weak points, all right? So this is just the upstream elevation, downstream elevation, and then the end elevation. That's actually the important part, because that is where the clay core actually sort of interfaces with the concrete. So let's focus just on that end elevation. If one actually looks at the bazometers there, again, you guys can see this is a very impermeable clay. It took a long time for the construction because the higher levels they actually built during one rainy season, so they basically captured a lot of moisture in the clay, and it's still basically dissipating after 25 years. If one looks at the earth pressure shells, you guys will actually see that one actually gets a decrease in earth pressures. And that is as a result of arch action that you actually arching that you get, because the concrete is built again with a slight angle, and then the earthfill is placed against that. But as we all know, earthfill wants to consolidate, it wants to settle, and because of the consolidation that one actually gets, and then you, as a result, you start getting these arching. So you start actually getting a reduction in your earth pressure around there. You guys can also see these seasonal patterns, all right? Those seasonal patterns are actually as a result of the expansion or contraction of the concrete due to thermal loads, all right? So if one actually looks at this effective earth pressure, it's a lot less than the design calculations that design took into account for stability purposes. So we actually have a lot less earth pressure against this concrete than what was actually taken into account in the design. And that's very interesting to take that into account. Okay. So that's basically my two case histories for earthfill embankment. Over to you, Manuel.
Okay, excellent. Thank you very much, Louis. And so let me go this presentation. I've got four examples in the case of embankment dams, and 4 examples with concrete masonry dams. But we'll just I'll just go for 21 minutes, and then I'll just stop when we get there. So let me find the screen. Okay, so I'm sharing now the screen. I hope that you see it again.
Yes.
Okay, excellent. So let's go for it. So example 1 is Caspe Dam, which it was commissioned in the late 80s. So the design was in the early 80s and construction works in the mid 80s, and it was commissioned in the late 80s or early 90s. And my relationship with this dam started off in 2008, I believe. And well, it's now like one of my children, because I've been just following her for all these years. And so what I wanted to share with you, this is a zoned embankment dam. So it's got a silty core. It's not really clay. it's more silty than clay. So very low plasticity. And the dam section has a very vertical filter. And it had quite a few issues in the design. So the contact between the gallery of the outlet works and the dam body was not properly treated. So it was not filled with concrete. It was compacted in a difficult manner. In some areas, it was filled with concrete, but others were not. So that right there was a weak point in this contact between this perimetral gallery, but then also the outlet works gallery that goes through the dam body from the upstream side to the downstream side. And also another problem is the filter for the dam was not properly designed, and it was not properly implemented. So, and this was noticed even during the construction. So the engineer was in charge of the construction for the ministry, who passed away a few years ago now. But during the construction, he noticed that the filter was not a proper filter. It did not comply with the empirical relationships between the material the filter is protecting, which is the core, the silty core, and then the filter itself. So you can see that this is what appeared at the crest of the dam, a sinkhole of several cubic meters because of an internal erosion process. And so here's some information. You can see this is 1990. So the year is 1990. And this is the seepage rates with pool levels. So these are pool levels, and this is the seepage rates that were collected in the weir, the total seepage. So the total seepage that was collected and measured, because this does not mean that the dam had more seepage, but this is what the monitoring system gathered. Of course, these were manual readings back in the day. You can see this is March 1990, and this is June 1990. And just have a look at this trend. We had this initial trend that was kind of linear, and see how during March and April, it really skyrocketed. So it really changed the trend, totally exponential. And you can see that, but by this point, so this is really weeks. So the last 2 weeks of March and the first 2 weeks of April. So within this month, of course, they noticed this, and they started grouting from the inspection gallery into the foundation. And you can see that they managed to change the trend in mid-April, even though it was still an ascending trend. And by mid-May, so like a month, 1 month of grouting works, they started more or less to tackle the issue. You can see that seepage rates dropped, then they went up again, up and down, but eventually by early June, they were lucky enough, and then the engineer who is retired, he retired also a few years ago, who was in charge of the grouting works. So not the designer, but the one in charge of the grouting works was a good friend now. He's retired in the south of Spain at the beach in Cádiz. but he told me that they were really lucky because they had no idea. They started grouting, trying different mixes until they managed to stop it. And this was caused because of this internal erosion problem, not just in the dam. So that picture I showed you, this is the crest of the dam, but also the dam had an old mine, water mine, in the reservoir that had a clog. Also, that collapsed with first filling, and they also had to grout. So they were losing water in the reservoir with this old mine that was connecting the valley of the reservoir with another valley. And so they had to grout that and make a concrete plug, and they installed bazometers and manometers that we're still monitoring today. So that's in the reservoir. So watch out for old mines, old tunnels in the reservoir area, but then also this. So this was at the crest, but the problem was deep down in the contact between the dam body and both the perimetral gallery and the outlet works gallery. So that was in the 90s, but then you can see that, well, in 2008, the dam has at the toe some drains at the toe of the dam, and these drains, so we monitored the water levels in these drains, and they started to go up and down. And so that caused like emergency works to do some additional grouting in the foundation, and of course we just we clogged and sealed those drains that they were at the toe of the dam. But then, so that was in 2008. In 2010, you can see this is the pool level, this is the temperature, the green is the rainfall, this is 2010, 2011, 2012, 13, 14, and just look at these bazometers in the foundation and how they start going up. See, this is 2013, and of course, reservoir levels go up, but and this bazometer, which in the past, well, I'd always shown a trend following the reservoir levels, but they really went up, and this was combined with, again, a lot of seepage. So we had to go also for grouting works. Just have a look at the seepage rates, and because of the grouting works with these emergency actions, how seepage drops at this point. So this is 2008, this is 2010, so this is 2 years. Just look at the seepage rates, how the seepage rates go. They really more than double in just a couple of years, and then grouting works, and then you can see this trend going up again. And if we have a look at the statistical model for specific bazometers, even though you can see here that just with the pool levels and the bazometer, it's well, you can see that it's very close to the reservoir levels. These are the absolute bathymetric levels, but it's not that simple to analyze the trends. And if you take one of these bazometers and you carry out a statistical model and you represent the residuals, that is the difference between the real readings and the forecast that your statistical model is giving you. So if you plot the residuals, you can very clearly see a trend. So this is 2004 and 5, 2005, 2006, 2007, and 2008. So when I did this statistical modeling in 2008, which is when I started working at this dam, just look at the trend with the residuals of the statistical model. So this is an example of how useful a statistical model can be, because this is very clear. And if you go to the readings, it's not that easy to pick up this trend. But the statistical model, if it's properly done, you can really pick it up. And this is just an example of what we had in the inspection gallery. And look at the water. So when we opened this bazometers, the clock, just look at the amount of material from the foundation. By the way, the foundation is really sandstone and marl, pseudo-horizontal sedimentary rocks, and with gypsum as well. And just look at the gallery as well. This sippage in the gallery, because of the pressure and how the material is really dragging silt from the core. So if you analyze this material is actually the core and the foundation. And so the problem with this dam, and by the way, last year, this dam, we had another sinkhole at the right margin. So again, the piezometers at the right, close to the right abutment, piezometers downstream and upstream of the core give you almost the same pressure. So there's no energy, no gradient loss in the foundation. And last year we found another sinkhole here at the upstream shoulder, but really caused by internal erosion down here. And look at this terrible design. The core is vertical here, but just look at how the inspection gallery is so close to the downstream toe of the clay of the core. Sorry, it's the silty core, by the way, of the core. So it's not in the middle. It's very close here to this drain. This filter does not comply with the empirical criteria for granule filters, and these are just the lines with same pore pressure levels. So you can see this is a dam with lots of issues where monitoring is critical. With all these emergency works that we've had in the last years, it's in total from 2008 up to now 4 emergency works, grouting with cement, but also with resins, So this last time, part of the grouting was done with resins. Every time we've done this emergency works, lots of piezometers have been lost, so new ones have been installed here from the gallery. So the inspection gallery can give you lots of trouble because of the gradients, but it's also a useful tool to install new piezometers and update the surveillance system. And we've installed new ones as well from the berms. So we haven't touched the core, but we've installed new piezometers from the gallery into the foundation and from the berms up to this point to control pore pressures here and here in the foundation, but without touching the core. Okay, next example, and yeah, perhaps I'll go very quickly now to see if I can give you a couple of more examples. This is a small dam, earth dam. You can see the foundation is really it's sandstone and weathered clays, but essentially sandstone and marl, pseudo-horizontal. So it's sedimentary. It's a sedimentary basin. This dam, but you can see it's very porous. You have little holes in the rock. This is the cross-section of the dam, very old dam, more than 100 years ago. The dam was built in the early 1900s, and you can see it's got some compacted clay and gravel here. This is clay, and then it has like a parapet wall. This is a cut-off wall, bentonite cut-off wall that was built in the early 90s. So the dam was undergoing internal erosion issues. And in the early 90s, from the crest, they built this cut-off wall, getting to this lower marl layer, because this is sandstone, but this is weathered clay. So this layer here is weathered clay, and you can see that the cut-off wall is into the marls. And so new piezometers were installed. Then in the early 2000s, when I started working at the dam, there was a lot of trees at the crest. We chopped them off. So you can see there are no trees now at the crest of the dam because we removed all those. And then these are the profiles that are with monitored. And you can see here how the piezometers, vibrating wire and standpipe piezometers, Casa Grande piezometers, and just open full water level piezometers down here, they were given a funny trends going up and down. And so I suggested the farmers to take advantage of when the water was low, and we inspected this area, and we went with a hammer, pounding on these blocks that are protecting the earth shoulder, and we found an area. So this is the upstream phase of the dam. We lowered the reservoir, and this is what we found. So we found a huge, several cubic meters, a hole in the upstream shoulder when we removed these concrete slabs that were protecting the upstream phase of the dam. And along with that, we carried out geophysics, upstream and downstream. This is downstream of the dam, and you can see these areas in the contact between these clays and marls and the foundation, areas where you can see that a lot of seepage is going on, because we have some galleries going through the dam body, and at those points in those galleries, they were not able to, this is the cut-off wall. So the cut-off wall could not, it had to stop here where we had the galleries. And they tried to complete that with conventional grouting. But these areas are areas where water was flowing. And so internal erosion was going on. So when we lowered the reservoir, this was upstream. This is what we found upstream, this huge sinkhole. And then downstream of the dam, we also cleared it up and we found this. And this is what the galleries I told you about. So water was flowing in this context. And this is what we've done to solve it. Essentially, we've created an inverted filter down here, downstream of the dam, and a way to filter and collect all the seepage and really stop the internal erosion from happening. And yeah, and then I'll just go very quickly. I'm not going to go into details. This is an example of an embankment dam, heightening of an old gravity dam. This is an example of inclinometers and how inclinometers let us know that something was going on, in this case, in the right margin, in the right abutment. This was a rise in the leveling of the old man. So the valley was having deformations, that it was we were having a lifting, heaving of the old dam blocks. So that's leveling here at the crest of this old concrete gravity dam, which is now like a massive plinth for the new heightening of the dam. And well, these were cracks in nearby buildings, and well, you can see these strands with also with rainfall and the velocity of the movement in the abutment. This is how the emergency action plan was triggered, and the dates, and because of rainfall. So this is the old dam. This is the right abutment. This is the old dam, the crest, and this is the huge, massive landslide we had All these people had to be evacuated. Inclinometers, bazometers were installed. And so all this earth was removed, remove weight from the top of the landslide, place it somewhere else, drain, get all these people out, demolish the buildings, and grout and hold this. This is the old dam, the crest of the old dam. And you can see all the work it took. The old dam, and this is the new dam, which is now here downstream. And so all these was monitored with inclinometers and bazometers, and thanks to monitoring, that could be managed. And this is an example, very quickly, of an earth dam founded on gypsum. So right here, this marl and gypsum. It's a wide core, and you can see also this how it's extended upstream, cut-off wall. But then with the first filling of the dam, you can see that this trend in the correlation, so seepage was skyrocketing in this area. And thanks to seepage and all the bazometers, this open standpipe and vibrating wire bazometers, we were able to portray and draw the lines with equal pore pressures in the marl and the gypsum layers. And then the cut-off wall in the foundation was extended. This is the left abutment. This is the crest of the dam. This is the reservoir. And the cut-off wall, that is this line, this black line here, it was extended here 200 meters. And you can see how, thanks to all these open standpipe bazometers here, these white dots, we could follow the lines with equal pore pressure. And thanks to the extension of the cut-off wall, where you can see that how the lines are together here, so the water, the gradients are no longer causing erosion here. And so this is just some pictures of that emergency works to extend the cut-off wall, and how the monitoring system was key to follow up and detect all these issues. And back to you, Louis. So these are the 4 earth dam examples. So the floor is yours again, if you want to
Thank you, Manuel.
With the concrete dams.
I will indeed. It's always, yeah, you call your first example your child. I think she's your auntie.
Yeah. Absolutely. Oh, by the way, at this last dam, La Loteta, I was in the construction of the dam in the early 2000s. So
Okay.
the construction of that dam finished in 2003, and I was in the construction. But this last dam, this very last dam I showed you, La Loteta, the one with a clay core, and so that was during first filling. And yeah, it's like your children. All these dams are like.
I think all the examples that we basically share with you guys today is like our children. So it's, yeah, I haven't used any example that I haven't been involved with. So these dams become part of as your children or your family. So some of them not such nice family to have. Give you lots of headaches. Okay. Let's look at some concrete dam examples. And I first wanted to start with seepage. And a lot of people don't see, well, in the environment that I work, don't consider seepage monitoring as essential with concrete dams. So listening to Manuel, I actually realized all my examples in the concrete side are actually arch dams. So my apologies to the gravity people. But on the concrete side, arch dams are my favorite dams. So typically in our environment, we have, this is the typical layout, and Manuel was talking about it. Yeah, in my world, dam owners normally don't like automatic installations and things like that. They want to have the manual ones. But just here's an example, for instance, a V-notch. And you guys can actually see that sediment that collected there. So you can imagine the flows that one actually determines. Look there, there's a permanent installation of the ruler, or where you read off, it's full of sediment. And so the readings that you get is just not correct. I mean, you get a completely wrong installation. But in any case, this is Naute Dam in Namibia. It was built in the era here in Southern Africa. So they built arch dams on any site. As you can see nowadays, most probably we would not build an arch on this site. So, but it's a very flat arch. I don't think there's that much arch action. It's sort of more, there's a lot of shear resistance that happens with this dam as well. Okay. But they've actually done some volumetric monitoring of the seepage. And at first, so the blue is the water level, and the red is converted to cubic meters a week. And they actually just monitor the pump. They pump out of a sump, and they monitor the pump volumes on a weekly basis. So I always ask people, if you now look at this, what do you make of it? And most people, when they look at it, say, well, there must be some or other connection between the water level going up and this going up. But it's basically 6 months later, if I can put it that way. So it's interesting. Namibia have this very distinct rainfall pattern. They only get rain from really from January to May. But normally January to April, that's when they get rain. They don't get basically no rain the rest of the year. If one actually just add some value to it and you highlight these peaks here, one actually sees that it happens during winter, our winter. So we're in the southern hemisphere, that's our winter. And if you consider an arch, what happens in winter, it's due to the seasonal temperature changes, it wants to actually contract, it wants to move downstream because it gets smaller. All right, and if it moves downstream, you normally actually get some movement on the upstream side, either in the contact between between the concrete and the rock, or in the foundation itself, or you could actually have a construction joint as well. But in any case, it's pretty obvious in this case, the upstream side actually opens up, and we get a lot more seepage actually through during that last period of the maximum downstream movement of the dam. But in many arches, if you actually know about arches, in many arches we actually do see this. So from now on, we will monitor it and see if there's any change, increase in seepage rates or not during the same conditions. All right, but that's one of the things, if you work with an arch, that you actually want to see whether your grout curtain is still functioning and whether you see something like this. Okay. So back to this dam that I showed you guys before, another arch dam here in South Africa. They actually do volumetric monitoring, okay? And if you also just look at that, very difficult to see. If you just go and add some value to it, you guys can see that it's actually the same. So just the interesting thing, one of the things that I use a lot is when I work with flows to compare seepage or so with each other, I actually use a log scale. Yes, you actually might lose some of the sort of the peaks and so on, but you can now compare it and you can actually see the two flanks also the same, but it's very small seepages, very much less seepage than what we've actually seen before. But the same thing. But the conclusion is that the grout curtain is still functioning here. It's just a slight increase actually in seepage during the winter time when the dam actually moves downstream. Okay. So that's the other thing as well. One of the Rolf Peck sayings is, and I grew up with this as well. No theory can be considered satisfactory until it has been adequately checked by actual observations. And that's one of the sort of the pillars of surveillance as well. All right. So yesterday I talked a bit on some swelling of concrete. There was a question about it, so I actually changed my presentation, the rest of it, and just focus on that, on the ASR, on swelling of concrete. So if you work with concrete that actually has some other chemical reaction that causes swelling, whether it's alkali aggregate or there's a lot of these reactions, but let's call it just swelling due to chemical reaction. There's some uncertainties that you actually, if you don't, it's things that you don't know about it. And so the first one, what's the current extent of the reaction or the swelling? The next one would try and get a feel, what's a future prediction of the swelling or reaction. Also, 3D behavior, especially if you work on an arch dam or where a three-dimensional behavior is important. We have some uncertainty about that. Also, what's the impact of openings on the swelling behavior? As I said, we've learned through the years when you have galleries and things like that, and you have swelling, you normally have cracking in where you have openings. And then also, what about the changes in stress profile? In the end, one, as Manuel was saying earlier, we need to make a prediction whether the dam is still safe now and whether it's going to be safe moving forward. So all these are like the uncertainties that we deal with to actually make these conclusions on the dam. So let's quickly look at Korabasa Dam again. All right. Very well monitored and instrumented. It's got, but for a dam of its size, that's what one would expect. I mean, it's a 170-meter high double curvature arch dam. And so the dam component itself have more than 1,300 measuring points. Okay. So these are all the loads and responses that are actually monitored at this stage. All right. And let's just look at the displacement and the strains. And I think it's very important, the issue of redundancy also will come out here, how important it is to have redundancy. And what we mean, a lot of people normally ask me, what do I mean with redundancy? It means that if you have more than one way to actually evaluate a certain component or a certain response, okay? Because Manuel was showing some values earlier as well. If you just have one piezometer and that piezometer goes up, sometimes the question is it the piezometer, is it really a correct reading, or is the piezometer actually going haywire, if I can put it that way? So that's part of the redundancy that we're talking. So let's quickly look at the precise leveling. You guys can see here's all the galleries in the dam, and let's just look at the top two galleries. They do some precise leveling. So let's look at the swelling rates between in a block where there's actually leveling points in both of them to determine the swelling rate over a period of time. So if one actually looks at this is in micro strain, the value that one gives here, okay? And if one actually looks at that, so one can look at, say, 38 maximum microstrain. But the first thing that one actually sees here is that you have different strain rates for the different blocks. Okay. And that one actually sees that a lot. Fortunately, in this case, they did really, they recorded the construction process really well. So we actually know they actually use different concrete with cementitious content for the different blocks. Okay, so we have that information, a direct relationship between cementitious content and the swelling rate. Okay, but that's the precision leveling. So they have rod extensometers to actually monitor also swelling. All right, they installed, first they installed these ones. okay? And these are the swelling rates. So that's the top ones. And as expected, as you go lower in the dam, the swelling rates will actually decrease because you have constraint. You have all the gravity and the weight on top of the section, the bottom section and the top section. So you expect not to have the same swelling rate. But even the top, if we go back there, it's the same that we actually have there. And the swelling rate there, you guys can see, is 30. And it's a lot less than the 38 that was measured by the precision leveling. Okay. So they also installed in these areas here, because you guys can see that actually they did some installations originally, but they went through into the foundation. They got some swelling there, but they were not sure whether the swelling is it movement in the foundation or is it just actually swelling in the concrete. So they installed basically rod extensometers just from the lowest gallery in the concrete part, so not into the foundation. Okay, so that we actually know, okay, it's just the swelling that's taking place there. So one would actually expect, isn't it? I mean, if you first looked at it, that the swelling that one gets there and the swelling that you get there should be the same. That's what one would actually expect. Okay. So remember, that's a swelling that I was showing you guys at the bottom level of the rod extensometer. But if we go and compare those new ones, you guys will actually see a lot more swelling. It's not, those ones were not comparable. Okay. And I'll explain to you guys just now why that is. There's also Carlson strain gauges installed all over the dam. All right. And if we just go and look at the top and we compare those, all right, you guys will also see that they are also less. But it's important that Carlson strain gauges have no opening on either side. They installed in the middle. So there's constraint from all sides. So if one actually goes and compare it, it's interesting to note that those rod extensometers on the one side, they actually extend from a gallery because that's where you take the readings. And then, so on that side, they're not constrained. So they can swell more into the gallery. So the one side, they're unconstrained, and then the rest of the side they constrained. Unfortunately, so that is why they actually swell more than what the Carlson strain gauges actually show to you. So if one actually goes and looks at the no stress strain gauges, this is typically, unfortunately, they only installed vertical ones. This is what you basically get there. If you go to the normal strain gauges, you can actually see the difference in stresses that one's measure in the section of the dam. There's basically 3 strain gauges installed. So closer to the upstream and downstream side, there's a lot more strain. In the middle where it's constrained, you actually see you don't have that much strain. And that's why you have these differences if you compare the different instruments. And that's why you also get, it's proof why you always get cracking into foundations or openings where you actually have alkali aggregate reaction. So just if one basically concludes here, those are the extent of the swelling rates, unconstrained swelling rates. There's definitely no decrease. It was built in the late 1960s, early 70s, and in the 90s, there was an extensive investigation analysis done, and that was concluded that it's busy decreasing, but I'll show you guys now with another case history why that conclusion was wrong. It's definitely no decrease. I showed you guys the effect of confinement, all right, and also the significant influence of openings. It actually allows the strain to increase in those areas of unconstrained, of lesser constraint, if I can put it that way. So, and that's one of the things that you have to take into account if you actually look at current rehab methods, things like slot cutting, all right? So if you now suddenly actually cut a slot into your dam that are under swelling pressure, just think what will happen, okay? And that's what you really see. That's where you, in many cases, over the long term, you actually get issues with these current rehab methods, okay? So Manuel was talking about the ambient vibration monitoring. I'll just quickly show with sort of the advantage of that. It basically, you determine the dynamic characteristics of a structure, okay? But we only use the ambient loads on the structure. We only, that's enough for us to actually determine the dynamic properties, all right? So we only actually measure accelerations and then we convert that into frequencies, all right? And it's really a relatively cheap way to understand, especially something like an arch dam, the behavior, the dynamic behavior of the dam. So there's my friend, Prof. Moyo from Cape Town University. He's really the expert on this here in South Africa. He uses very, very sensitive accelerometers that was actually developed for the space travel, okay? And so you measure the accelerations on the dam at each block. And as I say, you can actually convert that to frequencies and natural your modal shapes as well. So let's quickly look at Koga. I showed you guys before the arch dam that also have extreme ASR, and that's so this dam, one has to come up with a conclusion whether the dam is still safe or not. All right, that's very important. So let's just look at the vertical sort of swelling displacement, if I can put it that way. And this is what a lot of people use. So this is the vertical displacement on the center cantilever, and you see it with lots of dams. You see this this vertical swelling, and at a certain stage, the swelling appears to actually stop. All right, it doesn't appear to swell anymore, but I'll explain now why that happens. So this happens like in the early 2000s. But if one actually now goes to the quarter points here, all right, and you actually look at the horizontal displacement, in other words, the dam can still move up, you will see that the dam actually still moves upstream in the X and Y direction. So this dam is actually still swelling. It's just not vertically. You can't see the swelling rate anymore. I'll try and explain. So we went and actually installed crack meters, three-dimensional crack meters along there on each of the horizontal construction joints, all right? And there you guys can actually see the opening, all right? So if one goes and looks at, for that particular one, so this is the upstream and downstream movement. You can actually see this distinct opening here in 2003. So what we actually saw there is the joints really started opening up there. The whole joint is actually opened up in, you can see it there, and also the vertical displacement. You can also see this this movement in the horizontal construction joint. So the whole structure, it's not a monolith anymore, and it can't actually handle any more swelling. So the joint is opened up on the downstream side. All right. So this is, we actually did some this AVM measurement over there, and these are your different modes. So that's your first mode, your second mode, your third mode. Just of interest, so we had some results on the 3D crack gauges that we could not actually interpret because they were moving vertically, and we could not, it did not make sense from a normal point of view. So we thought there's something wrong. But actually, if you actually see these from the results of the AVM, actually showed us that yes, those blocks are actually moving up and down as well. Okay, so they actually lose if the water level drops. These blocks, because of the swelling, they becomes really cantilever, and the top part are actually moving. All right, so let me just, okay. So basically, if one combine these, and again, it's the redundancy. So we had some uncertainty with some of the results. Looking at them all together, suddenly we can actually, we see there's asymmetrical arch behavior. There's definitely cantilever action in winter during low water levels, which is really a big concern. And we could also conclude the difference in foundation stiffness. All right. I think I've basically talked about that. So Manel, over to you. Sorry, I've also gone a bit over on my side.
No problem. No problem at all. So I think, let's see, it's 11:10 our time. So how much more time do we have left? 20, half an hour?
I'm getting confused with the time difference here. Sorry.
Yes, I'm a little bit messed up now with, I don't really know how much more time.
Yes, we still have around 50 minutes.
Oh, 50.
50.
It's 3:40 here, and
okay.
We have the session till 4:30. So
Okay.
we still have 50 minutes approx.
Okay.
Okay,
No,
great.
sorry. So we were rushing unnecessary,
You
to be
both are
honest.
absolutely on time, well on time.
Okay, no, but that's excellent because that gives us a bit more room. Okay, so let me go. Yeah, we were absolutely rushing through the presentations. Okay, so let me go back.
Manel, somehow me and you got our calculations wrong. To be honest, I also thought we had less time.
No, but that's good because that way we're going to have enough time for discussion, which is also important. I mean, being able to go back to the presentations and then addressing any comments, or that's also important. So it's good. We're gonna have enough time for that. Okay, so I'll go now for additional examples of arch gravity. Well, in this case, it's really gravity and arch gravity dams. So it's a good thing because it really complements the examples that Louis has shown you. And so this first one is really an RCC dam. So it's rolled compacted concrete. It's a gravity dam. It's pretty high. It's over 100 meters high, and you can see the spillway. This is the downstream phase. You can see by the car, more or less the size of the dam. And this is a platform, an elevated platform of 20 meters. So the foundation is way below. This dam is founded on an alternation of sandstone and marl. And I started having a relationship with this dam as well in 2008 during first filling. So in 2008, it was really the first filling of the dam, and I was lucky to be involved in following and doing the surveillance on the monitoring reports during first filling of the dam. And in this area of the left abutment, several massive seepage started off in this area. You can see there were no trees back in the day. So in 2008, these trees were very small. And the problem is the water started bypassing. There's a fault in this area, exactly where when I'm in this area, there's a fault. And water was going through that fault, and we had springs. So we had water springs down here. And you can see here that water is still collected. And massive grouting works went on. And the problem is sandstone is really, really hard to be grouted. It's very difficult to grout sandstone rocks. And so all the grouting works, tons of cement and grout were going into this fault, this joints in the rock, and it was useless. So all these water springs here, we couldn't stop them. The only thing is, because of the cementation of this sandstone, there are really no internal erosion or erosion concerns. And so what we did is we placed a rock fill with gravel and essentially an inverted filter here. So this is all covered with an inverted filter that is protecting any kind of erosion from happening, and water is just flowing and it's collected, and the seepage wears down here, and happy days. So here's some additional pictures. So this is an example of these weirs. On the left and right abutments, both abutments have seepage. It's more intensive in the left one that I just showed you in the previous picture. You can see that it's labeled. These are triangular. This is a rectangular one because it's bigger, and they're numbered. And all this seepage is collected in quite a few of these weirs, outdoors weirs. So they need to be readily and weekly cleaned up and maintained. And of course, we need to compensate for rainfall. When we have rainfall, the seepage rates change and are affected by rainfall, so we have to compensate for that. And this is an RCC dam. And just have a look at this is one of the galleries. So one problem we have here is this is not the RCC concrete. So this is like a precast concrete that is really covering the real concrete of the dam. So it's very difficult for us to carry out visual inspection here, because even the joint meters, so this is block 0 and this is block 2. And so the joint meters are not all the way trustworthy. They were not trustworthy because they were anchored to this precast concrete and they were not in touch with the actual RCC concrete behind. So what we did, we had to drill and make sure that our joint meters really went into the real concrete of the dam, so that we were measuring openings and displacements of the joints in a real manner. Another tip from this dam is look at these pipes. So this is the dam body drainage connecting one gallery with another. So this is the top of this gallery and it's connecting with the bottom of the upper gallery. So we're connecting this water, and in order to prevent a lot of carbonate deposits from building up, just look at this pipe, how it's turning here, and look at this inverted siphon here, see? So this turn in the pipe is making that this water, which is dam body drainage, as opposed to the one from the foundation. So this is from the dam body. Thanks to this turn, the air from the gallery is not going into the pipe. And this is preventing a lot of carbonate deposits from building up here. So all the dam body drainage is this way. And by the way, this dam has a lot of carbonate deposits. So every other 5 years, we re-drill the drainage system in the foundation. It needs to be re-drilled because it's just clogged. It gets clogged because of the limestone and the carbonate deposits. So you can see in the gallery, you can see this. This is part of the. This is one of these clogs because every of the 5 years, there's grouting and re-drilling. So you have machinery in the galleries all the time. This is the old river diversion clog. Watch out for river diversion clogs. When you have these concrete clogs, oftentimes you have seepage, you can have pore pressures building up. You want to monitor river diversion clogs, especially in old dams. And this is always unusually forgotten. It's a tunnel somewhere there in the abutment or deep down. Nobody has gone there in decades. There's no lightning. It's full of rats and snakes, whatever. So make sure the river diversion clogs, make sure you have proper lighting. This lighting was installed so that we could inspect this tunnel and get to the clog and make sure that you can monitor this both visually, and if you have some piezometers there, well, even better. Okay, now this is the cross section of the dam. You can see it's the Japanese cross section for earthquake. So it's very sturdy and very stable. So this block number 2 is located right here. So this is an up downstream view of the dam. And these are thermistors installed in contact with the water and with the air. And this is the temperature at a certain moment. So you can see going from 15, 8, 12, 17, 13, 14. So this is the temperature here. And if we have a look over the years, so this is 2008, this is 2008, 10, so this is 2 years. This is 2007, 12, 14, so this ends up in 2014. It goes from 2007 to 2014. This is the downstream area of those thermometers, and this is the upstream in contact with the water. And these are we call them external, so pool levels, temperature, ambient temperature, and rainfall. Rainfall is the green. Remember, this is 2 years. So you can see here, this is every year. So summertime, winter time, summer, winter, summer, winter. And so 1, 2, 3, 4, 5, 6, 7, 8, 9 years here. This is the evolution of pool levels. Like I told you, 2008. See, this is first filling of the dam. This is the first filling of the dam right here. This was a flood event. So the pool level came up here. But so first filling and then the evolution. It's an irrigation dam. And have a look at the temperature, how it's still from the construction, heat from hardening of the concrete is still dissipating many years after the construction has ended. So you see it's 2015 and you can see this trend in the thermometers and you can see it's still going down. So heat is still dissipating many years after the construction. This is upstream, is a bit more distorted because of the thermal action of the water from the reservoir. But you can also see this trend going down and how the air temperature and the water, the pool levels, how that is affecting the evolution of the thermometers inside of the dam. Obviously, other thermometers right here, the temperature is very constant here. So in massive dams like this one, the temperature here is very constant all throughout. Also, that is affected by the presence of galleries. So when you have a gallery like this one, this area of the dam is dissipating heat, and this is affecting how the dam is reacting, how the dam is behaving, how deformations are going on in the dam and inside the concrete. In this dam, there was a huge concern for a transversal joint here. So, longitudinal joint. So apart from the block joints, this vertical joints, along the dam, from one margin to one abutment to the other, they were concerned about a crack being created here because the dam is massive. There's a lot of surface in contact with the foundation. And when this is not constrained because of the foundation and also this heat and heat dissipation after the construction, there was concern about a crack building up here. And so leaving this like two different blocks in between. As a matter of fact, another dam that I showed you in a previous presentation, this dam had a joint, but created during the construction here in the middle of the block, and this joint was grouted after the construction to give back the monolithicism of the structure, because it's such a massive dam. In this case, this joint was not implemented during the construction. Again, remember, it's not a transversal block joint, but a joint that goes from one abutment to the other here in the middle of the cross section. So in this dam, this joint was not implemented, and long base crack meters were installed here in the dam body, just to make sure that this crack did not happen. And indeed, it was good, and thanks to the heat dissipation, that did not happen. So no cracking was involved. You can see here the also lines with the same temperature. This focus on thermometers is because of cracking, and this internal cracking in the dam body that can prevent the dam from behaving like one big element. And so you can see upstream and downstream and how the temperature is evolving with pool levels and then with the temperature. This is 2013, 14, 15, and 2018. So, well, you can see, well, just a few years here in the analysis. Then in the foundation, because of these sandstone and marl layers horizontal in the foundation, there was concern about the circulation of water and in the foundation. So you can see that not just piezometers close to the dam body and foundation interface here, but also deeper down were installed. You can see that these piezometers, we have frequency hertz, we have pressure, we have absolute piezometric level, meters above sea level, and then percentage of pressure in relationship to the pool level that you have in that exact moment. So if we have a look at the plots, these are pool levels. This is the annual temperature. So again, summertime, wintertime. These green bars are rainfall. This is the pressure of those piezometers in kilograms divided by square centimeter. This is the piezometric level, so column water. Absolute, this is the pool level. So this blue line is the pool level, absolute pool level, meters above sea level. And these are the piezometers, absolute meters above sea level. And this is the percentage of load in relationship to the reservoir level. You can see that they go from almost 0 to, in some cases, more than 50, 40, almost 50% of the pool level. So if we represent that also in the cross section, you can see that this block 11 is right here. So it's towards the left abutment. This is the left abutment. This is the right abutment. The dam is very long. So it is, this is really this part. You can see that this would continue here. This block 11 is this one. So in this block, you can see that we have the pyramidal gallery that is connecting with this horizontal gallery. So that's why we have the horizontal gallery, and this is in the perimetry. This gallery that goes from this abutment all the way down and up here, up to this point. So it's this block, and these piezometers, these are the piezometers we have here. And if we represent this slope, you can see that it's not linear. It's not really following the typical linear. And this is a trend that we find in real dams, that the uplift pressure low is not linear, and when it gets to the drainage gallery, you always would have here a break in the lines, but then this is kind of parabolic. So it's linear here, then when you get to the gallery, and then it builds up until you get to the downstream toe, and this is a parabolic low, and up to this point, well, we consider it to be linear. And this is downstream's view of the dam, the blocks from downstream. This is the spillway. And if we represent the absolute piezometric levels of the piezometer, so this, we are representing this. So this is the pool level, and this is the absolute piezometric levels of the piezometers. We can see exactly where these pressures stand in relationship to this is the pool level this day, this is the pool level that day, and these are the piezometric levels. These blue lines are the piezometers closer to the foundation, so to the dam body foundation, this, and the red lines are the ones underneath. So these red lines are the ones underneath, and the red ones are the ones closer, the blue ones, the ones closer to the contact. Okay, next example. Next example, I'll go quickly. Another RCC gravity dam. In this case, we have conglomerates. You can see downstream phase of these RCC dam with quite some seepage. Also a lot of seepage here from coming from the contact in this abutment. This abutment does not have as many seepage. You can really tell by the vegetation. Some cracking at the crest. Again, this area in the right abutment with lots of vegetation and seepage, even trees. This is what the dam looks like on the inside. You can see the galleries with a lot of seepage. These conglomerates, the cement from the conglomerates, watch out for this. You can see this being dissolved and being dragged into the dam. A lot of moisture all over the place. So the monitoring sensors, seepage weirs, and pendulums, we have lots of issues with moisture. The galleries give us direct access to the foundation. Even now we have manganese deposits, and this is the foundation drainage. But you can see that it's a good opportunity to have access to the foundation from the galleries. By the way, foundation drainage, this, and you can see here from the top of the gallery, these pipes that are coming down from the ceiling. This is dam body drainage. This is dam body drainage, and this is foundation drainage, and the pumps. This dam and another one in Algeria. These is the pumps. These are the pumps in the gallery that it's in the perimetry of the dam, deep down. If you have a power supply issue and these pumps stop pumping water, you get your this lower gallery. So this is the gallery in the perimeter down here. This gets flooded if those pumps don't have a proper backup. You can see these are the joints. This dam had massive, it was RCC of first generation, so they did not make joints. So these joints were 60 meters apart, and the dam, obviously the concrete cracked. So every 15 meters, the concrete cracked, and these cracks are controlled with crack meters, and they have not evolved in 20 years. But this is a good lesson. If you don't make joints every 15 meters, the concrete is going to make them by itself. This block, you can see direct and inverse pendulum. So during the first filling, the dam went downstream up to 25 millimeters. So this dam is 80 meters high. Just look at the amount of dam body that is in the foundation. So this is the foundation. This is downstream, but a big part of the dam is founded to get to the sound rock. So it's 80 meters. This gallery is great because it's very close to the upstream toe, so it's very efficient when it comes to drainage. You can see 3 levels of galleries. The displacement mainly due to deformation in the foundation, because this concrete is way more rigid than the foundation. So during first filling, the dam moved up to 25 millimeters downstream. Nowadays is only moving from the annual range is from 5 to 8. So it's not as big. This was during first filling, reservoir levels, and the horizontal displacement. This is the vertical settlement, so leveling. Again, it's the foundation is not the dam body because it's an RCC dam. It's the foundation because of the weight of the reservoir. It's settling. You can clearly see how this strand, all the primary, secondary creep in the rock. So the joints and the family joints in the rock, that's accommodating the weight of the water of the reservoir, the weight of the dam. And throughout, from first filling in the 99 up to 2011, you can see this very clear trend. And this is the evolution of pool levels throughout the years. So first filling really started off in 2002. This is when first filling happened. And you can see it's a beautiful, it's by the book, how the foundation behaves. Again, there's lots of bazometers in the foundation to control. And we see this parabolic law. When you get to the gallery, these poor uplift pressures go down, but then from there to the downstream toe, you have a parabolic law. And very quickly, this example is another gravity dam. This is not RCC, so this is conventional vibrated concrete. You can see lots of galleries, 1, 2, 3, 4, and 5 levels. You can see lots of galleries all over the dam. These are the joints, the joint meters. So you can see the opening of the joint meters in millimeters, 0.8, 0.07. So the different evolution of the openings of these joints. And then look at this, rod extensometers into the foundation. This one's tilted. This is the absolute values with millimeters, but just look at this beautiful behavior. This is first filling of the dam, 2011. So, but really 2012 was the first filling of the dam. But you can see, so this is during the construction. And if you have a look at the evolution of millimeters of this rod extensometer, so this sensors here, you can see how it goes from 0 and it's slightly, look at this gap. So during these years, nobody was there to measure, and so no information, but you can see that it's beautiful and wonderful how the foundation is the forming with the weight of the dam. And when you place the dam and you finish the construction, the dam has the joints in the rock mass are accommodating, and you have this consolidation, this primary and secondary consolidation. Of course, you never want to get to the plastic, and you want to have an elastic behavior in the foundation. But just look at this beautiful behavior, and look at this. When we finish the first filling of the dam, just look at these extensometers. How we have these jumps here, boop, due to the first filling. This is the opening of the joints and how it's following the thermal and the opening, and how they also react to the first filling of the dam. Again, opening shear of the joints. This is the leveling at the crest of the dam. So vertical settlement at the crest of the dam. So time series, all the topographical milestones on the crest, and just have a look how with the before first filling is really the thermal reaction of the concrete, and you can see that it's swelling a little bit in the summertime, then it's volume contraction in the winter time, and the leveling at the crest is really capturing that. So it's up to 2 and 3 millimeters. But then with first filling, just look at this. With first filling, you see how the dam goes. This is really having some going down because of the deformation of the foundation. Beautiful. And to wrap it up, this as another dam, this in this case is an arch gravity dam in the Pyrenees, limestone foundation, beautiful, beautiful, gorgeous dam. This is limestone. So a few years ago, we had this drought, very, very high temperatures, very hot. And so reservoir levels went down drastically. And this is a look of the galleries when we go from the dam into the rock. So no water, all dry. And this is the inverted pendulum all the way up to the crest from the foundation. It's right there in the middle of the dam. This is the cross section. You can see it's an arch gravity 1, 2, 3, and 4 levels of galleries. So you can see this is the gallery in the perimetry of the dam, and then 1, 2, and 3 levels of galleries. So, and this is the highest gallery at this elevation, and these are the central blocks. And remember the pendulum, the inverted pendulum. So you can see this is the different reading plates. Beautiful. This is the downstream, upstream direction. This is the one abutment, one of the other. You can see that the this one is very, very controlled, usually less than 2 millimeters. But you can see this year's pool levels really go down. The temperature goes slightly up because of this drought, and just look at the evolution. You can see this trend. See, this is the reading plate at the crest is an inverted pendulum. Look at this trend. So from 2014 to 2018, it's almost 5 millimeters, and the dam is going upstream. So the dam is really like kind of swelling because of these heat waves. And also look at what happened in this central block. Of course, the joints are grouted, but we found a horizontal crack that appeared, and it goes from the upstream face to the gallery. So this crack is limited really in this area. So it's in this area. It goes from the upstream face to the gallery. And thank God it has not evolved. So it's right there. It has not evolved from when this happened because of this drought and this heat wave. But well, you can see that this is now closely monitored, and it has not evolved. But yeah, we can have issues like this one in our dams, and that's it. That's the presentation. So I think we're in time, and for a good discussion with you. If you want to comment on something, if you want us to revisit any of the presentations, whatever, we can have a nice discussion now if you want.
Daniel, can I maybe just propose quickly something? Can I put something
Yes,
on the
sure.
screen?
Absolutely.
And you should know this. So me and Manuel presented, had another presentation earlier this year for another forum. And I thought it's maybe just a good summary of what some of the most salient points that we actually were talking about. And I'll make this slide available as well. But yeah, I mean, it's, and maybe we can quickly just go through there. So yes, we've been hammering it that visual inspections, most important component of dam surveillance. Redundancy in all your systems is very important. Then the other thing, the quantity of data. So that's the one thing. If you go automation, you'll most probably have huge quantities of data, but just remember that it's not to say if you quantity is not a measure of quality. If the more you have, the more effort you must actually put in to make proper interpretation. And maybe you see it as well, Manuel, but I've seen it where dam owners go for automation. You end up, nobody looks at it. They have these alleged automatic systems, but there's no human intervention. Yeah. So, and that's also, there's this tendency to accumulate more data and less effort in the creation of information, knowledge, and insight, really. And then we talked about data processing, evaluation, and dissemination, how important that is. Manuel spent a lot of time on the risk analysis and the input from dam surveillance. That's what we're really trying to do with dam surveillance. Remember, and I was also talking about uncertainty right in the beginning and managing uncertainty, but we normally use risk analysis for that. And then the other important thing, yes, it's very good that we have all these new technologies. Most of them actually use some or other form of digital equipment. But remember, most of these equipment actually have a relatively short lifespan. So if you go to a system like that, you have to budget and you have to plan to actually regularly replace it with new equipment. And remember, you have to have the right your personnel should reflect it as well. I've showed you copies where they struggled. They don't have the right people actually working there. So if you go for new technologies or automatic systems, you need to make sure that these people, that you have the right contract or people to actually maintain it, to look after it, and that you don't have a breakdown in your monitoring system. And I don't know if you want to add anything to that as well, Manuel. Sorry that, yeah.
No, absolutely. I fully agree on all those points, and I think we've stressed the importance of being cautious with automated systems, and the human factor is always very important. And so I fully agree on that. And
okay.
Let's see if someone wants to comment something. Ask whatever. So we are here at your disposal.
Thank you, Mr. Luis. Thank you, Dr. Manuel, for making excellent detailed presentations. Now, shall we start for the question answer session? And may I request to the participants for their questions, please?
Maybe I can just add, sorry, seeing that at this stage nobody has a comment or a question for us. But the last concrete dam that I mentioned, and sorry I rushed it a bit, but so the plan is actually because we've reached a stage where we consider that dam not to be safe anymore, that Arch Dam, Kouga Dam. And the idea is to actually build a structure in front of it and to actually use the old Arch Dam as basically just as shuttering, if I can put it that way. But yeah, so that's sort of my one example. Most of the other examples, we're still just evaluating the performance of the dams, but that one, unfortunately, the dam owner, well, there's a new decision maker at the dam owner, and they made a political decision not to do anything. They think it's fine. So it's interesting if you if you have decision makers that don't understand the technical side of things. But in any case, so they've been made fully aware of it. And they've decided not to do anything about it. So hopefully it won't be a malpassé or so, to be honest. But in any case, it's really getting to a stage where the integrity of the structure is not reliable anymore. Any comment? Any question?
Do we have any questions from the participants, please? They may ask.
Yeah, I think there's one question on the chat. Latest technologies for the repair of Stilling Basin floor. Repair was done with epoxy treatment, but cannot stand with high rate of flow of water. Any suggestions, please? Yeah, Stilling basins, when you have very high speed flows over the concrete, yeah, the epoxy treatment can be just removed. Mm-hmm. And so there are really no latest technologies for this. So if you have massive erosion and the grouting and the treatment, so epoxy is really for the surface. Yeah. If you have something going on at a deeper level in the concrete, you really have just to demolish that partially and then anchor. You need to place anchors and also think about monitoring that. It's difficult to know without having a drawing, but Stilling basins, oftentimes you can have uplift issues combined with even with the flow itself. And so you need to know how the anchors are doing, and also if there are some uplift pressures that are dangerous. So probably monitoring that Stilling basin, looking for any type of swelling, tilting of the walls, of the side walls of the Stilling basin, and also if it's very deep, you can also do some bathymetry to know how that is evolving. And but if it's really a huge problem, we have some good examples in the US and in Portugal as well. Eventually, you have to stop the overflow in water and really demolish that and rebuild it almost from scratch. But it really depends on the example. Also, the mythical example in Africa of the scouring downstream, and so Stilling basins can be very, very critical in some cases.
But yeah, I 100% agree with you, Manuel. And I mean, the other thing with Stilling basins is also, it's actually normally a hydraulic problem that causes you these high flow rates. And I mean, in a lot of cases, your erosion is caused by some vortex flows, if I can put it that way as well, or actually loose material in your stilling basin as well. So there's some other things that you can actually look at. And sometimes if you just do some hydraulic work on it, maybe a model study and some numeric modeling, you can actually solve the problem with fairly simple, small additional structures, but just get the flows. As I say, the main thing that causes you actually erosion in stilling basins are normally your vortex flows, if I can put it. And something like epoxy, I mean, I don't even want to use epoxy. A lot of people use epoxies on surface of spillways, even an uncontrolled spillway, because you've got some flaking of the concrete. I've never seen it work. It never works. It's we've tried all the international firms' latest and greatest solutions for that. It will work for a year or 5, and then it normally comes off, because it's also the different properties, and especially the thermal properties between the different materials that normally, or the properties between the epoxy and the concrete. Eventually, it wouldn't last in that condition.
Yes.
Any other comment, question?
You're very welcome. Yes.
Any further questions? I think no. Please.
Yeah, I don't know if that's good or bad, because maybe.
I think all the participants have very clear concept. The doubt has already been cleared. That could be the reason they don't have any further questions. But still, if the participants still have any questions, they may write to us, the organizers, EBIP. We will get back to you with the respective speakers and with the respective answers, and we'll get back to you over the email. So I would like to convey my special thanks to Mr. Louis Hatting and Mr. Dr. Manuel for sparing their valuable time for conducting the 2 days virtual session on dam surveillance. I'm sure all the participants have benefited from their vast knowledge shared during the program. This topic requires a week's period for understanding the whole concept with visual inspection of the dam. We would love to do the physical program once the COVID-19 pandemic situation will improve and lift out the restrictions of travel from other countries. Dr. Louis and Dr. Manuel, sir, we look forward to your support in this regard when we will organize this session on physical mode in future. Thank you. Thank you to all the participants. Thank you so much. Stay safe, stay healthy.
Thank you.
Thank you very much.
Thank you.
I'm looking forward to seeing you soon.
Thank you, sir.
In person.
At least hopefully we'll see you when you are hosting the ICOLT in New Delhi in 2024.
Absolutely, sir.
Yeah.
Thank you.
We love to host you.
Thank you.
Look forward to see you soon. Thank you.
Thank you, everybody. Have a great day.
Bye-bye, everybody.
Goodbye. Thank you.
Goodbye. Goodbye. See you soon.
Okay, thank you. Bye-bye. Sir, thank you.
Thank you, sir. Thank you, Ji.
Thank you, Gwaji.